Welcome back to G Fun Facts Online. Today we are looking deep into the cosmos, at a discovery that feels almost poetically timed for a celebration, yet represents one of the most violent events the universe can produce. We are talking about a structure technically cataloged as RM J130558.9+263048.4, but which astronomers have rather charmingly nicknamed the Champagne Cluster. This is not just a pretty picture to put on a desktop wallpaper. This object is a crime scene. It is a snapshot of a cataclysmic collision between two massive galaxy clusters that occurred hundreds of millions of years ago, and the light is only just now reaching our sensors. This discovery was announced right around the turn of the new year, fitting for its nickname, but the name implies more than just timing. It describes the physics of the event, a cosmic bottle being uncorked, spilling energy and matter into the void in a way that is revolutionizing our understanding of how the universe is built. To understand why this is such a big deal, we have to start with the scale of the players involved. We are talking about galaxy clusters. These are the titans of the universe. They are the largest structures in the cosmos that are held together by their own gravity. When we say cluster, do not just think of a group of stars. Think of a city of galaxies. A single cluster contains hundreds, sometimes thousands of individual galaxies. For context, our own Milky Way is part of a smaller neighborhood called the local group, which is slowly drifting toward a much larger structure called the Virgo cluster. But here is the fascinating part that trips people up. The galaxies, those shining islands of billions of stars like Andromeda or the Milky Way, are actually the smallest part of the cluster by mass. If you looked at a galaxy cluster and weighed it, the galaxies themselves only account for about 1% to 5% of the mass. So what is the rest? The vast majority of the normal matter, the stuff made of protons and electrons, the stuff you and I are made of, exists as something called the intracluster medium, or ICM. This is a soup of superheated plasma. It is hydrogen and helium gas burning at temperatures of nearly 100 million degrees Celsius. It is so hot that it does not glow in visible light. It glows in X-rays. That is why we cannot see the full majesty of these clusters with our eyes. We need space telescopes like NASA's Chandra X-ray Observatory to see this glowing gas. But even the galaxies and that superheated gas combined are dwarfed by the cluster's true master, dark matter. Dark matter makes up roughly 85% of the cluster's mass. It is the invisible halo, the gravitational glue that holds the fast-moving galaxies and the hot gas together. Without dark matter, the cluster would simply fly apart. There is not enough gravity from the visible stuff to hold it. So you have these three components, the galaxies, the hot gas, and the dark matter. Now imagine taking two of these massive clusters and smashing them together. That is what happened to create the Champagne Cluster. It is the most energetic type of event in the universe since the Big Bang itself. The Champagne Cluster is what astronomers call a post-paracenter merger. In orbital mechanics, the paracenter is the point of closest approach. That means we are looking at the aftermath. The two subclusters have already smashed through each other and are now racing apart, leaving absolute chaos in their wake. This gives us a rare opportunity to see how those three components, galaxies, gas, and dark matter, behave differently when they crash. This is the physics of dissociation. Think of it like this. The galaxies are like ghosts. The stars within them are so far apart relative to their size that when two clusters collide, the galaxies just fly past each other. They do not physically touch. They pass like ghosts through walls, guided only by gravity. The dark matter behaves the same way. It is collisionless. The dark matter halos of the two clusters pass through each other effectively ghost-like. But the gas is different. The gas is a fluid. It has pressure, it has viscosity. When the two massive clouds of intracluster gas collide, they slam into each other like two water balloons meeting in mid-air. They experience drag force, known as ram pressure. They slow down drastically and they heat up to extreme temperatures. This creates a separation or dissociation. The dark matter and the galaxies continue speeding outward, maintaining their momentum, while the gas gets stuck in the middle of the wreck, lagging behind. In the Champagne Cluster, X-ray maps reveal a massive peak of superheated gas stranded between two clumps of galaxies. This separation is actually considered a smoking gun for the existence of dark matter. We can literally see the gravity of the invisible matter pulling the galaxies away from the visible gas that got left behind. But the visual spectacle, and the reason for the Champagne nickname, comes from the shockwave. When these clusters collided, they were moving at supersonic speeds relative to the surrounding gas. We are estimating speeds exceeding 2,000 kilometers per second. That is over 4 million miles per hour. When you move that fast through a medium, you create a bow shock, exactly like the sonic boom of a jet or the wake of a boat moving through water. In the Champagne Cluster and similar giants like Abell 3667, these shockwaves are colossal. They can span millions of light years, stretching larger than the clusters themselves. As this shock front travels outward, it compresses the tenuous gas of the intergalactic medium. This compression does two things. First, it heats the gas, making it shine brightly in X-rays. Second, it acts as a giant cosmic particle accelerator. Protons and electrons bounce back and forth across the magnetic fields within the shock front. This is a process known as diffuse shock acceleration, or Fermi acceleration. These particles get accelerated to near the speed of light. When these relativistic electrons spiral around magnetic field lines, they emit something called synchrotron radiation, which glows in radio waves. For years, astronomers have theorized that the cosmic web, that vast filamentary network of gas that connects galaxy clusters across the universe, should be glowing with these radio waves, lit up by shock waves. The Champagne collision provides one of the clearest views of this phenomenon we have ever seen. The radio emission traces the shock front like a neon sign, outlining the invisible magnetic skeleton of the universe. The specific shape of the Champagne cluster is what really captivated the scientific community. We have seen collisions before, like the famous bullet cluster, which has a very clean bullet-like shape. But the Champagne cluster is messy, it is turbulent. The radio relics, those glowing arcs of radio emission caused by the shock, appear twisted and fragmented. They resemble the effervescence of bubbles rising in a glass, or the chaotic flow of liquid spilling over a bottle. This complexity suggests that the collision was not a simple head-on smash. It was likely an off-axis merger, a glancing blow that set the entire system spinning and tumbling. These bubbles we see are likely regions of low density, where the magnetic fields have expanded, pushing the hot plasma aside. By studying these bubbly structures, astrophysicists can map the magnetic fields of the intergalactic medium, which is a property of the universe that is notoriously difficult to measure. Understanding the strength and orientation of these magnetic fields is crucial if we want to understand how the universe evolved from a smooth soup of particles after the Big Bang into the structured web of galaxies we see today. It helps to compare the Champagne cluster to other famous cosmic pileups to really appreciate it. You have the bullet cluster, which is the gold standard for dark matter proof, clean, high-speed, classic shape. The Champagne cluster is messier, likely older, and shows us the turbulence that follows the crash. Then you have Abell 3667, which hosts one of the largest shockwaves ever seen, stretching 6.5 million light-years. The Champagne cluster shockwaves are comparable in scale to that, suggesting we are seeing a merger of similar titanic energy. Then there's Abell 1758, which is often confused with the Champagne cluster, but is actually a quadruple merger, two pairs colliding at once. That represents the chaotic future that the Champagne cluster will eventually settle into. We also have to remember that this collision is not happening in isolation. It is occurring at a node of the cosmic web. The universe is structured like a sponge or a neural network. Vast voids of nothingness are surrounded by thin filaments of dark matter and gas. Galaxies flow along these filaments like cars on a highway, heading toward the massive intersections where galaxy clusters grow. The shock waves from the Champagne collision are propagating into these filaments. This is a crucial area of study. By observing how the shockwave illuminates the filaments, astronomers can measure the density and temperature of the cosmic web itself. This is often referred to as the Warm-Hot Intergalactic Medium, or WEM. It is thought to hide about half of the normal matter in the universe, which has been missing from our census of stars and galaxies. The Champagne shockwave acts like a flashlight, revealing this hidden matter for the first time. The unveiling of this cluster was a triumph of what we call multi-messenger astronomy. We needed different types of eyes to see the whole picture. We needed NASA's Chandra X-ray Observatory to provide the high-resolution maps of the superheated gas, the fluid that lagged behind. Without Chandra, we would not see the dissociation that proves the existence of dark matter. We needed radio ears, ground-based arrays like the Meerkat telescope in South Africa or LOFAR in Europe. These played the key role in detecting the Champagne bubbles and the shockwave itself, because they are sensitive to that faint synchrotron radiation from the accelerated electrons. And we needed optical witnesses, telescopes like the Subaru telescope or Hubble, to map the location of the galaxies and use gravitational lensing to map the invisible dark matter. So what happens next for the Champagne cluster? The collision we see today actually happened hundreds of millions of years ago. In the eons since, gravity has begun to win the battle against the outward momentum of the crash. The two subclusters will eventually slow down, stop, and fall back together. They will pass through each other again and again, ringing like a bell, each time stripping away more gas and damping the shock waves. Eventually, billions of years from now, the two cores will merge into a single, massive, spherical galaxy cluster. The beautiful radio relics and shock waves will fade, and the violent Champagne effervescence will settle into a quiet, hot equilibrium. But for now, for us as observers, the bottle has just popped. The Champagne cluster offers a perfect laboratory to study the extreme physics of the universe. Magnetic fields stretching millions of light years, particles accelerated to the brink of light speed, and the invisible scaffolding of dark matter that holds it all together. It serves as a stark reminder that the universe is not a static painting. It is a dynamic, violent, and evolving movie. The serene pinpoints of light we see in the night sky mask the tremendous energies at play in the deep cosmos. Events like RM J1305 demonstrate that the processes of creation are still ongoing. The cosmic web is still twitching, growing, and snapping into place. As we enter a new era of astronomy, with even more powerful instruments like the Square Kilometer Array and the Athena X-ray Observatory on the horizon, we can expect to find many more such champagne moments, shocks and flows that reveal the hidden pulse of the living universe. So, here is a toast to the Champagne Cluster, a shockwave in the dark, a light in the void, and a spectacular beginning to a new year of discovery. Thanks for listening to G Fun Facts Online.